The number of bacteria in a culture decreases according to a continuous exponential decay model. The initial population in a study is 8,700 bacteria, and there are 4,611 bacteria left after 14 minutes. For part A, we are being asked to let t be the time in minutes since the beginning of the study, and let y be the number of bacteria at time t. We will need to write a formula relating y to t and use exact expressions to fill in the missing parts of the formula and to not use approximations. So the continuous exponential decay model that we are going to look at is here, and they filled in some pieces for us, but essentially we have y equals y sub 0 e times e to the power of r times t, which y is our final amount, y sub 0 is our initial amount, times e, and then all raised to r, which is our rate, and t, which is our time. Okay, so the first thing that we're going to do is identify what we already know, and this is given to us in the description above. It says our initial population in the study is 8,700 bacteria. So y sub 0 equals 8,700. There are 4,611 bacteria left. So our final amount is 4,611. And our time, our t, is 14 minutes. Okay, so using this model, we're going to plug our known values in, and we will get 4,611 is equal to 8,700 e times e, all raised to r, which is our rate, that is unknown, and 14, which is our t. Now our goal with this is to find our rate, because essentially what our rate is, we have the initial amount, 8,700, and we have our final amount for 14 minutes of time. But we want to know, the rate, because if I wanted to know the final value of bacteria at any time, all I would have to do is plug in any time to that t value, which is currently 14, but say I plug in 6 instead, and because I know the rate that the bacteria is, in this case, decreasing because it's a decay model, so this rate should be negative, then I can find the final amount of bacteria at any point in time. So that is the reasoning behind this. So we are going to solve for r. And to do this, we are going to divide 8,700 on both sides, because we want to get e by itself. All right, so this is going to cancel, and we are left with, on the left-hand side, 4,611 divided by 8,700. And we set that equal to e times r times 14. Now we can reduce the fraction on the left in our calculator, and we end up getting 0.53 is equal to e raised to the power of r times 14. Now we need to get the r, we need to bring the r times 14 down. So we're going to use the natural log on both sides. ln of 0.53 is equal to the natural log of e raised to the power of r to the 14. R times 14. Now, ln to the e is just 1. So we can rewrite this as the natural log of 0.53 is equal to r times 14. Now to get r by itself, all we need to do is divide by 14 on both sides. And we get r is equal to the natural log of, 0.53 all over 14. But we're not done yet because we just found the r, and this is what we're going to be plugging into this spot right here. So our final answer for part A is y is equal to our initial amount, which we said was 4,611. Or I'm sorry, I did that backwards. Our initial amount, which is 8,700, because y sub 0 is our initial amount. E times e raised to the y that we just saw. I'm going to erase this so we have more room. Oopsies. Raised to the rate that we just solved, and that was, what did I say? ln of 0.53 all over 14 times t. And this is our equation for A. So now, if we plug any value into t, because we know the rate, we can find y, which is the number of bacteria that we want to know at a given point in time. So let's do that. Let me erase this so we have more room. Because all we really need is our equation from above. So in part B, we are asked how many bacteria there are 15 minutes after the beginning of the study. So copy down our formula, y equals 8,700 times e raised to the power of ln, the natural log, times 0.53 over 14, and then multiply that by 15, because that is our t. Okay, now all we really have to do is use our calculator and plug in this number, ln times 0.53 over 14 times 15. And we end up getting a number that I already put in my calculator earlier. We end up getting, oh no, this tablet's going crazy on me. We get y equals 8,700 times e to the power of negative, and that makes sense because it's a decay model. So we are going down in bacteria growth, negative 0.680226205. So long decimal there. But then from here, we also just plug this value into our calculator. I just don't want to make any rounding errors, so I use that entire number. And we end up getting, this is equal to 4,406.568661. And in the problem, it says round your answer to the nearest whole number. So we're going to round this to 4,407. And that should be our answer. And let's check to see if that makes sense. So the initial population in the study was 8,700 bacteria. And after 14 minutes, there's 4,611, so relatively half. So in 15 minutes, we should have a little bit less than 4,611, and we have 4,407. And that is less than 4,611, so that is our answer. And that is how you solve a continuous exponential decay model